In this lecture, I'll cover the basics of binary representations for numbers, along with how characteristics of these representations impact decimal numbers and the way that they're used in calculations. Modern computer systems rely heavily on binary representation. In particular, all numbers are represented by a series of memory cells, which can occupy two discrete states of high and low voltage. Numbers are stored as sequences of these cells called registers. The low or high values for each cell are discretized to represent a series of binary bits. The number of bits available within a register directly constrains the values that can be represented. First, let's define some terms that will make this discussion as consistent as possible. When working with values stored in digital systems, the most common grouping is a series of 8 bits referred to as a byte. When binary numbers are written out, it's very common to display them in groups of 4, sometimes referred to as nibbles, which makes them easier to read. We usually don't use these 4-bit chunks in practice, however. They're just written this way for convenience. The smallest chunk of data you'll generally be working with is a byte, and all variables will be represented in terms of bytes. Now, one thing I want to try to do here is make the notation very clear going forward, because working on multiple number systems can be a bit weird. So when discussing numerical calculations, I'll try to maintain a consistent notation and terminology. First, we have to be able to translate between binary and decimal numbers. Since binary numbers can look like decimal values, a subscript is usually provided to denote between the two. For example, a binary number will be given a subscript of 2, and a decimal number will be given a subscript of 10. Another term for the number system or number base is radix, which is encountered a bit more in programming. I'm going to consistently refer to any number in any base as a digit, and will reserve the term bit when referring specifically to binary or base 2 digits. In general, I will try to reserve the term digit for decimal numbers, but may have to use it more generally when explaining things. I will use the subscript to differentiate between number systems whenever the value is ambiguous. One thing to note is that it is possible for binary numbers to have fractional components, as in this last example. In this case, the point separating the integer and fractional parts is referred to as a radix point. You most commonly hear this as a decimal point when working in the decimal number system. I want to briefly discuss how to move between binary and decimal representations. The broader point here is to convince you that the mathematics are identical between number systems. This will let us demonstrate several principles using decimal numbers that we're more comfortable with, and we can trust these concepts carry over to binary arithmetic. Let's first look at converting from decimal to binary numbers. This can be done using a simple multiplication and addition sequence that is colloquially known as the double-dabble algorithm. We start with a register x initialized to 0. We then read the binary number from left to right. For each binary bit, we double the register and add the value of that bit. Let's take a look at the sequence 1, 1, 0, 1. We initialize our register to 0. Then consider the first bit, multiplying our register by 2, which is still 0, and adding 1 gives us a decimal value of 1. The next value is 1, so we double the register, which currently has a value of 1, and add 1. This value of 3 is then assigned to the register, overwriting the initial value. The next binary bit in the sequence is 0, so we will double the register and reassign the new value, 6. Finally, we double the register again and add the last bit, 1, to get the final representation of this binary number, which is 13. Now let's look at a longer 8-bit value, 0, 1, 1, 0, 1, 0, 1, 0. First, we initialize our register to 0. The first bit encountered is 0, so the register doesn't change. The next bit sets our register value to 1. Doubling this value and adding the next bit reassigns the register value to 3. Doubling that reassigns x to 6. Doubling and adding the new bit 1 gives us 13. Doubling gives us 26. The next one gives us 53. And finally, doubling the last bit, 0, gives us the final decimal representation, 106. The conversion from decimal to binary follows the opposite path, but is generally a bit more difficult to do in your head. To convert from decimal to binary, we use the remainder method. This method iteratively divides the decimal number by 2 and records the remainder at each step. Once the number is reduced to 0, the remainders provide the corresponding binary value for the original number. Let's look at the conversion of the decimal value 13 into binary. We'll start with the original decimal value 13. We then divide by 2 to get 6 with a remainder of 1. We record the remainder. And then divide the result by 2 to get 3. Since there's no remainder here, we record 0. We then divide this result by 2 and get 1 with a remainder of 1, which is recorded. Finally, we divide by 2 to get a result of 0 and a remainder of 1. Reading the remainder values from top down gives us the binary representation of 13, which is 1101. So far, all the values that we've considered were positive numbers. In mathematical expressions, the value we want to express can take on negative values. Let's consider the number negative 17 in base 10, which has a corresponding representation of negative 10001 in binary. We have to somehow encode this negative sign so that it can be stored in a digital register as part of the number. The easiest way to do this is with the sign and magnitude format, which uses one of the available bits, known as a sign bit, to store the sign of the value. The most common representation uses a 0 to represent a positive value and a 1 to represent a negative value. So there are two possible binary representations for a number with a magnitude of 17. The binary representation for a positive 17 has a leading 0, and negative 17 has a leading 1. While the sign and magnitude method is simple, it isn't often used to represent integers. However, this method is particularly important when we move to the more common floating point formats, which do leverage a sign bit. The two most common signed integer methods are 1's complement and 2's complement. These have some advantages over sign and magnitude, particularly in the area of computational efficiency, so I'll go over them briefly. For 1's complement, the leading bit still identifies the sign of the number. However, the corresponding negative or positive value is represented by applying a binary NOT operation to all of the bits. For the numbers with a magnitude of 17 from our previous example, the positive value has the same representation as the sign and magnitude counterpart. However, the negative value is calculated by applying a bitwise NOT operation to all of the registers. For another example, look at the binary value for 122, which is 1111011. We can calculate the corresponding negative value by flipping all of the bits in that binary number. With 2's complement, which is more common representation, the corresponding negative values for a number are calculated by taking the bitwise NOT operation, just like 1's complement, but also adding 1. Again, the positive value has the same binary representation as 1's complement and sign and magnitude. To get the negative number with 2's complement, we apply a bitwise NOT and add 1. Note that the result of the bitwise NOT operation is identical to the corresponding negative representation in 1's complement. The final result is the 2's complement binary representation of negative 17. The same process works for our second example of 122. 1 is added to the 1's complement representation, giving the final 2's complement representation for negative 122. The next representation I want to cover is known as fixed point. This method isn't directly used in practice, but is necessary for understanding the floating point values that are commonly used in science and engineering. In fixed point, a fixed number of bits are allocated to both an integer and fractional part of a number. To understand this format, we have to first understand how fractional representations can be incorporated into binary. Like decimal, the integer and fractional components are separated by a radix point. The consecutive places to the right of the radix point represent the half, quarter, eighth, and 16 places consecutively. So, given the binary number 1101.1011, we can calculate the resulting value by addressing the integer and fractional components separately. To do this, we first independently evaluate the integer component by converting the bits on the left side of the radix point. This represents the whole number component 13. We then convert the fractional bits to the right of the radix point to get 11. This value is the numerator for the fractional component. Since the 4-digit fractional component goes out to the 16th place, the final fractional part is 11/16. Now I'm going to wrap this video lecture up by going over basic binary arithmetic. My primary goal here is to convince you that the mathematics play out identically, independent of the number system used to represent these values. We'll look at the two most basic operations for arithmetic, addition and subtraction. If we want to add two binary numbers, we apply the same process used for traditional addition, realizing that the value after 1 is 1, 0. Therefore, when we add these two operands, the first step involves adding 1 and 1, which yields 1, 0, the binary form of 3. The rightmost value is therefore 0, and we carry the 1 to the next space to the left, just like standard addition. By continuing this process, we can find the final sum. When we convert all of these binary values to decimal, the results are identical, and there's a 1-to-1 mapping between the operands and the result. Multiplication works the same way. Here, we can multiply the two operands 100.01 and 1.01 by using a method similar to the familiar long multiplication algorithm. Once we've multiplied each of the digits in the second operand, we add the intermediate results to get the answer. Once again, this provides a perfect correspondence with the decimal multiplication. However, note that the intermediate results aren't necessarily going to be the same. One operation that you may not have encountered in traditional algebra is the modulus operation. This operation is given by the modulo operator. So here the term is stated as A equals X modulo Y. In C and C++, the modulo operator is the percent sign. The modulus of two operands, x and y, is specifically the remainder of x divided by y. So, as an example, the modulus of 73 and 7 is 3, because 73 divided by 7 is 10 with a remainder term of 3. The result of 13 modulo 3 is 1, since 13 divided by 3 is 4, with a remainder term of 1. The result of 15 modulo 5 is 0, because 5 evenly divides 15. I wanted to briefly cover this operation because it's commonly used in numerical methods, such as when we want to generate random numbers. It's also the result of a particular quirk that we'll encounter with unsigned integers, or integers that don't use negative values. When dealing with discrete numbers, one issue that must be addressed is what happens when the result of an arithmetic operation exceeds the maximum possible value that can be represented. The resulting behavior is most often referred to as overflow. If you have an 8-bit unsigned integer, the maximum representable value is 8 ones, which converts to 255 in decimal. If 1 is added to this number, the numerical result is 256. However, storing that number requires 9 bits, which are unavailable. For the most part, overflow behavior is undefined. You should not expect any consistent results if overflow occurs in your code. However, overflow behavior in C and C++ is defined for unsigned integers. When overflow occurs for an unsigned integer data type, the n least significant bits are stored, where n is the size of the register. So if we add two 8-bit operands resulting in an overflow, the 8 least significant or rightmost values are stored in the result. This behavior is actually mathematically equivalent to taking the modulus of the result with 2 to the n, where n is the size of the register. In this case, if x is the result of the addition, the value stored in the output register is x modulo 2 to the 8, or x modulo 256.